And we're back to the Project SINAG Colloquium 2023. Some additional reminders: raise your questions during our questions and response segment. You may write them via the Q&A tab, which you can find in your Zoom screen. With your question, kindly include the name of the study or presenter to help us identify who should provide you with a response. Some few reminders. We also have to receive your certificate via email, you have to fill out the evaluation form to be sent out in the Zoom chat after the event. Now, I know that some of you have really prepared for this moment to showcase your research on solar PV and geomatics. To begin this next half of our program, we will be hearing from Ms. Charlotte Gavina, a BS in Electrical Engineering student from Pamantasan ng Lungsod ng Maynila, and from Alexandria, Athena Era Dizon and Jerwin J. Escosio, BS in Geodetic Engineering students from the University of the Philippines, Diliman. They will present their research outputs during their month-long OJT term.
Good morning, everyone. I'm Charlotte Justine, an on-the-job trainee of Project SINAG from Pamantasan ng Lungsod ng Maynila. It's a pleasure to be here to share our research findings on comparing solar PV output forecasting in the Philippines, solar irradiance with and without weather parameters. Now let's walk through what you can expect from this presentation. I'll start by exploring the background, research gap, and its significance. I'll also clarify the scope and the limitation. Moving on to methodology, I'll explain how we collected the data, the pre-processing steps, and the XGBoost modeling process. And of course, how we evaluated the performance of the models. In results and discussion, I'll interpret the findings. Finally, I'll conclude by summarizing the key outcomes and offer some recommendations for future research. In the Philippines, a nation increasingly focused on sustainable energy solutions, the importance of accurate solar PV output forecasting cannot be overstated. With renewable energy initiatives gaining momentum and a commitment to reducing carbon emissions, our country is recognized as an emerging player in the global PV market. While some literature suggests that solar irradiance is a key factor in PV production, other studies recommend the inclusion of weather parameters to enhance forecasting accuracy. Therefore, the central question is, does the incorporation of weather parameters enhance the accuracy of solar PV output forecasting in the Philippines, or is solar irradiance alone sufficient? So the objective of this study is to determine if weather parameters improve solar PV output forecasting compared to using only solar irradiance. The significance of it lies in its potential to optimize energy utilization and enhance grid management. In the wider context, it contributes to the realization of Sustainable Development Goals, the SDG 7, ensure access to affordable, reliable, sustainable, and modern energy for all. Before we proceed, let's clarify the boundaries of this research. The study is centered on the Philippines, specifically Pangasinan in Luzon, Negros Occidental in Visayas, and Davao del Norte in Mindanao, focusing on data collected between January 2020 to December 2021, specifically during daylight, 8 a.m. to 5 p.m. The machine learning algorithm that will be used is the extreme radiant boosting, since it has gained prominence in solar power forecasting because of its superior performance compared with other machine learning techniques. The data for solar irradiance and the 10 weather parameters, wind speed, wind direction, relative humidity, temperature at 2 meters, high, low, medium, and total cloud covers, and total precipitation were collected from ERA 5, while the production was sourced from solar PV installation sites from the 3 locations I mentioned earlier. Here are the summary of the datasets used in this study. From these data, production and weather parameters, principal component analysis was conducted on weather parameters to reduce data dimensionality, addressing multicollinearity without significant information loss. After using the initial components that accounted for the most variation, this will be referred to as the principal components. At this stage, we now have the two predictors, solar irradiance alone and the principal components. We applied XGBoost forecasting using a five-fold nested cross-validation approach. This process involving model training, hyperparameter optimization, model testing, and validation were repeated to obtain the final optimized model. So now we have two models, M1 using solar irradiance and M2 using solar irradiance and weather parameters. Finally, we evaluated its performance using mean absolute percentage error, and so we have the output, forecast model accuracies. The application of principal component analyses streamlined the selection of weather variables obtained from RFI for inclusion in Model 2. Through this, the original 10 weather parameters are condensed into 5 principal components, each accounting for a cumulative proportion of 80% or greater of the total variance in the data. This was observed for all sites. Also, the MAPE values recorded from the validation fold form the basis for assessing the improvements achieved by Model 2 over Model 1 in terms of predictive accuracy. As you can see, these values represent the average forecasting errors for each location, allowing for a direct comparison between the two models. Notably, in Pangasinan, Model 2 25.951% outperforms Model 1 29.85%, while in Negros Occidental, Model 2 31.051% demonstrates slightly improved average MAPE value compared to M1 31.683%. Furthermore, in Davao del Norte, Model 2 34.723% exhibits significant improvements over M1 40.861%. Earlier, I presented this question. Does the incorporation of weather parameters enhance the accuracy of solar PV output forecasting in the Philippines, or is solar irradiance alone sufficient? We address this by conducting a comparative evaluation of two models, Model 1 solar irradiance and Model 2 solar irradiance and weather parameters using XGBoost. And from the results presented, M2 generally outperforms M1 in forecasting solar power in Pangasinan, shows minor improvements in Negros Occidental, and significantly outperforms M1 in Davao del Norte. Take note, you should be aware that these studies forecasting models' performance is influenced by data quality, location, and prevailing weather conditions, introducing potential uncertainties and variability that can impact solar PV output predictions accuracy. Therefore, it's important to understand that the study's findings are specific to the data set and locations analyzed and should not be extended to other regions or time periods with different weather patterns. Thank you for your time and attention today. In closing, I'd like to emphasize the key takeaways from our discussion. We've explored a comparative analysis between relying solely on solar irradiance and integrating various weather parameters to enhance solar PV output forecasting. As we move forward, this study offers the practical benefit of improving the accuracy of solar PV output predictions, which can significantly impact the planning and management of solar energy systems. It's an exciting step towards a more sustainable and resilient energy future for the Philippines, where solar power can play an important role in addressing energy needs and mitigating environmental challenges. Now I'm open to any questions or insights you may have. Thank you once again for being part of today's presentation.